Welcome back to this course on C programming and assembly language. We are in module 4, and in the last couple of lectures we looked at implementing a function like printf that handled one variable number of arguments and two variable kinds of data types as well as function parameters which are passed to that function. So now moving on with our analysis of because of the assembly translation that happens in a certain way that we have studied till module 3, what is the impact on the high level programming language, right? So in that regard, in this lecture we are going to discuss the following: recursion versus loops. So anyone who's worked with C programming or C++ till now would have used recursion at some point or the other, and recursion is a programming concept which is a very useful tool because it just allows us to think of the problem in a very hierarchical manner, and all you have to do is call the same function again and again with fewer and fewer arguments as we go along, right? And the only thing is to ensure that you have one exit criterion so that you don't go into an infinite loop, right? So let's look at a simple example first of all of what recursion is and how the same thing could be implemented in a loop. So let us look at implementing a factorial function. So what is this? Let's say for example I want to evaluate m equals n factorial, right? So if I were to implement this using a loop, then this is how it would happen: int fact of int n, and I would say int answer equals 1. I'd create another loop variable I and simply say for I equal to 1, I less than or equal to n I plus plus, and answer into equals I, right? And then return answer. Okay. On the other hand, if I were to implement the same concept using recursion, then I would simply do the following. I would say m is equal to n into n minus 1 factorial. So all I have to do is int fact underscore recursion of int n, okay? And what we are going to do is, let's just go ahead and implement the factorial as it is first. We'll just say that return n into fact underscore recursion of n minus 1, okay? Of course, the problem here is if you start with a positive integer, then at some point you will hit 0 and then you will hit -1, -2, and you will go on and on and on. There is no end to this recursion here. So therefore you have to give a stopping criterion, and that is very obvious. If n is equal to 1, right, then we say return 1, else return n into fact of n minus 1, okay? So this is not a very complex program. So let's go ahead and look at amongst these two implementations which one is bound to be faster, especially for large numbers, right, large n. So let us take the recursion example first of all, okay, and I'm going to translate this to its assembly equivalent, okay? So I will say int fact underscore recursion of int n, and I will say if n equal to 1, return 1, else return n into fact underscore recursion of n minus 1. Okay. And instead of doing an unoptimized assembly translation, I am going to go ahead and implement this directly in assembly language. Okay. So let us translate this to the assembly output, right, object code. Okay. So first of all, the bracket here would get translated to the prologue. Okay. And what is the prologue? It is first push EBP, right, and then move my ESP, whatever the ESP value is, move that into EBP, right, and then subtract ESP comma some constant. Okay, let us call it 0x40. Now this is my prologue. Then I go ahead and implement this particular functionality. Okay, how will this code get translated? Remember, I am not doing a line by line translation, I am implementing this directly in assembly now. Okay. So what do I have to do? I have to first take the value of n, okay, which let us say is contents of EBP plus 4, right, or EBP plus 8. So what do? I am simply going to say move into EBX, okay, contents of EBP plus not 4, 8. Okay, and my Y8, because n is stored in EBP plus 8. Okay, n is going to be contents of EBP plus 8. So I am simply getting the value of n into my BX register, then I am going to subtract, or I will just decrement, I do not have to subtract, I will decrement EBX. In the process, if EBX were 1 and I decremented it, then it would set the 0 flag, and I will say jump on 0 to return underscore 1. Return underscore 1 is a label, so I will put that somewhere down here. Okay. Return underscore 1. Okay. What do I have to do in this place? All I have to do is to simply move EAX, because if I have to return the value 1 from the function, I have to load EAX with the value 1 and simply say return. So why don't we go ahead and initialize our EAX here, comma 1. Okay. So this is init EAX equal to 1. Basically I am saying the return value is initialized to 1 already. So if I want to come here, I am just going to say RET, because when I come here, EAX already has the value 1 in it. Okay. Now suppose the operation of decrementing EBX by 1, right, did not result in 0, right, and let us assume that only a positive number is being passed to this function. Okay. We are not going to check for that condition here. Then it means that I need to implement the other part, which is basically this portion here. Okay. Now this portion will translate to a call as shown here. Okay. So what is that? I need to simply multiply the value of n with a call to the same function with an argument n minus 1, right. So therefore what do? already my EBX should have the value n minus 1. So, if I just say push EBX, right, this should do because it already has the value of n minus 1, right. This is basically passing n minus 1 argument, and then I will say call fact underscore recursion. Okay, so let me do one thing, let me move this guy a little below here. Okay, this return 1 I will move here. Okay, and this label is called return underscore 1. Okay, so I am just going to call fact underscore recursion here, and when I return from this function, EAX should have the return value, and therefore all I need to do is to multiply this EAX with the value of n. Okay, so what do? I simply will maybe I will just move ECX comma n, okay, or I will say EBP plus 8, okay, and then I am going to say I mul of ECX. So, what is this doing? It is essentially loading ECX is getting the value of n here, okay, and this step is simply saying EAX is n into fact of n minus 1. So, this is the optimized assembly output of this particular recursion call, right. Now, on the other hand, if you go ahead and look at the implementation of the factorial function for loop, right, it is the C implementation is shown on the left, right, what I wrote earlier, and if you look at the assembly translation, right, it is not very different. So, this is again our the prologue, right, then this is just initializing some variables, and then I have a couple of moves, and I am doing a jump, I am doing a multiply, and so on. So, if you look at the assembly output of this loop implementation, it is not very different from what we had in our recursion call, right. You have a compare, you have a jump, and then you are doing some multiplications and so on. However, the difference lies in the number of instructions that get executed eventually, and this will become evident when we look at the stack more closely. So, let us look at the picture of the stack when I go ahead and call this function in the main. Okay, I am going to say fact underscore recursion of, let me call 3. Okay. So, if I look at the picture of the stack here, just look at the number of operations that are involved when we are implementing a function using recursion. So, if I want to call fact underscore rec of 3, right, this will simply translate to push 3 call fact underscore rec of 3, okay. No, there is no of 3, it is just calling the function, and after I return here, let us say I have a variable n equal to, right. So, I will say int n, right, then I will simply have to out here, after I return from the function, I will move into n the value of EAX. This is the assembly translation, right. So, if you look at this, the value 3 gets pushed onto stack, and then you are calling fact underscore recursion, and this is my return address. Let me assign a variable, a label here. So this return address will get pushed onto stack when you implement the call fact underscore recursion. When you call this function, this particular return address gets pushed onto stack, right? And then you go into the implementation of the fact underscore recursion. As we saw, there is a prologue that gets executed, right? So the EBP of main will get pushed onto stack. Okay. Then what am I going to do? I am going to move my EBP, to where ESP was, right? So my EBP will point here now. Okay. Then I am going to subtract some local variable space. This will be my ESP, right? This is the first call of fact underscore recursion. Now you check if the value of n is 1. Well, it isn't. So then I am going to call the function again, right? So, and I am going to call the function with the argument 2 this time, right? So I am going to push onto stack the argument 2, right? And when you come here, you will have the return address of factorial function that is defined there, okay? So if you look at this guy, it's essentially what we are doing is we are implementing this particular call now, okay? So this will be my return address fact. This is the address it has to return to after finishing the call, right? So that will get pushed onto stack here, okay? Then again my EBP of my EBP of fact underscore recursion for the first call will get pushed onto stack. EBP fact, I will just say first call, right? That will get pushed onto stack, okay? And then you are going to move my EBP into this particular point here, right? And then ESP will again get moved offset here somewhere. Now again you come into this function and then you check if the value of n that has been passed to this function. Now what is the value of n? It is this value 2. You check if that is 1, well that is not 1, and therefore you again decrement this value and then call the recursive function again with the value 1 this time. So what do? You again push onto stack, so this is my thing, I am going to push onto stack the value 1, okay, and again I am going to call it with the particular return address. Okay, and then I am now going to again move my push onto the stack, this EBP fact 2, right, and then I am going to repeat this process again and again. Of course, this time the argument that has been passed to this factorial function is 1, and therefore I will simply do a return of 1, which means EAX will get loaded with 1, and then I will execute the epilogue. By the way, in the previous case here, right, if you look at this page here, what I have not shown is the implementation of the epilogue, right. What is the epilogue? It is basically simply going to undo these operations, right, before I return. So out here I will do, so it's not this, So out here I have to execute the epilogue and then do a return, right. Without undoing the prologue, I cannot get out of the function, and therefore the label return underscore 1 has to point to the epilogue. And what is the epilogue? It is nothing but add ESP comma 0x40, right, and then pop EBP, and then the return instruction will happen accordingly. Okay. So now you come here and then you see that, okay, the argument n is equal to 1, and therefore I just need to do a return of 1. So you will move into EAX the value of 1, and then you will execute the epilogue and then come back to this particular stack here, right. You will return from here, come here, then return from there, come here. So what we say is, ultimately the operation that has to be performed is a very simple multiplication, right. But in order to do this single instruction of imul with another register, what we are in turn doing is executing the prologue and epilogue for every call of this function, right. So conclusion is, the prologue and epilogue is an overhead for recursion. So on the other hand, if you look at the loop implementation, it is actually very straightforward, because we are doing just what is necessary. In the sense, we are multiplying, and accumulating this product, right, over the loop, and we are not having to call any function in this process, right. So therefore there is no prologue or epilogue overhead when we implement the same function in a loop, right. So and remember, the prologue and epilogue is not a very simple operation, because all of these are memory operations. They involve the stack, right. You have to push the EBP onto stack, then you have to subtract the ESP with some value, which is not too bad, right. Then during the call you have to push the return address onto stack, then you have to pass parameters again, right. Each parameter that I am passing has to be done through a particular push, and so effectively, apart from the prologue and the epilogue, there is also a parameter pushing, right. So prologue and epilogue, I will also add parameter pushing. Prologue, parameter pushing, prologue and epilogue is an overhead for recursion, which is not there in loops, and therefore it is a common practice to take a program that has been implemented using recursion and convert it to a loop if performance is extremely critical, right. So these are some implications that we have at an assembly level, and we are able to appreciate them very well, because we understand exactly what happens at the lowest level in machine language, right. So in the next lecture we will look at more such examples of speeding up programs or performance analysis of certain assembly implementations for certain special functions.